So within the nuclear unit, it's important to take a look at elementary particles. And so um, when we did the nuclear unit, we took a look at the general structure of atoms, and we looked at radiation and the forces. But with elementary particles, we can go deeper, and that's what we're doing here. So some particles that we looked at so far, right? Protons, neutrons, electrons. We also looked at in radioactive decay positrons, which are positive electrons. It's the anti-particle of an electron. Neutrinos, as well as anti-neutrinos. And so, we've looked at all of those. Um, Now, in the 1950s, they started to detect particles from the sun, and at that point, they also started to smash particles together, and all of a sudden, we don't just have protons, neutrons, and electrons anymore, and these basic particles of radiation, but we're detecting all these other particles, and so um, the reason we don't see these particles is that in ordinary matter is because they're very unstable and they decay quickly. And so we don't, it's very hard to not only detect them, but also to study them. Now we know of hundreds and hundreds and hundreds of particles, and, they've categorized them. And we're going to take a look at some of the basic ones here for which fall under the standard model. So an elementary particle is elementary because it's not made of any smaller parts. And so we have three types. We have quarks, we have leptons, and then we also have exchange particles. And these are the categories that we'll look at. Now, on your equation sheet, under the nuclear section, it's section 7.3 in the current curriculum. You actually have this table right in there, which is pretty awesome. They give you a lot of information here. There's 6 types of quarks. We have the U, which is the up quark, C, charm quark, and then T is the top quark. Each of those have a charge of positive 2/3 E. We have the down quark, the strange quark, the bottom quark. All of those have a charge of negative 1/3 E. Remember, E is the elementary charge, right? So 1/3 of that would be 1/3 of the elementary charge. And we have that there. Each quark has its antiparticles. So for instance, with the up quark, the anti-up quark, you put a bar on top of it, would actually be a charge of negative 2/3 E, not positive 2/3 E, and it has the same amount of mass. So what I want you to try to do, you can pause the clip, go ahead and write down what the antiparticle of the down quark would be in terms of charge and mass. Okay, so you should have gotten a charge of positive 1/3 E, same mass as the down quark. Now, if you remember Large Hadron Collider, we know a hadron is made out of quarks. So 3 quarks together make a baryon, and a quark plus an antiquark make a meson. And so a proton then is a baryon, and we can work that out. So a proton is made up of an up quark, another up quark, and a bottom quark. So if we add those up, right, we have a positive 2/3 E plus a positive 2/3 E plus a negative 1/3 E. We add those up, positive 4/3 E plus negative 1/3 E, so we get a total of positive E, right, which is what a proton is. So what I want you to try, you can pause the clip and give this a try. A neutron is an up quark plus a down quark plus a bottom quark. Go ahead and add up the charges and give that a try. And then when you're ready to check, you can hit play to continue. All right, so we should have, positive 2/3 plus a negative 1/3 plus a negative 1/3, and therefore it's 0 charge. Okay, so we add up the charges of those quarks, which are located in the neutron, and that's what we get there. All right, so the baryon number is also something we need to consider with quarks. And if you notice on the right-hand side over here, you have the baryon number. And every quark has a baryon number of 1/3. And then each antiquark has a baryon number negative 1/3. And so let's get the baryon number for a proton. So a proton is UUD. So, we have 1/3 plus 1/3 plus 1/3, baryon number of +1. Okay. Now, if we have an antiproton, which is a anti-up quark, anti-up quark, anti-down quark, we can find the baryon number for this. And so if we do that, right, we have a negative 1/3 plus negative 1/3 plus negative 1/3, -1. So let's go ahead and do this for a meson, which is made up of quark and an anti-quark. Well, let's do an example of that where we have, let's say, for like this particle here, a quark and an anti-quark. Well, it turns out, right, we would have a positive 1/3 plus a negative 1/3, and its baryon number would actually be 0. So what's the point of this? The nice thing with that is that in all reactions or decays, the electric charge and the baryon number are conserved. So not only electric charge is conserved, but the baryon number. So for instance, if we added or brought together an antiproton plus a proton, let's say we combine those two, right? Well, we know the charge of a proton is +1. We already did that. The charge of an antiproton is -1. So if we bring those together, we end up getting a charge of 0, which means that they annihilate each other. And so what happens there is actually that mass turns into energy. And so nothing exists then except for energy. That is called annihilation. Now, if you look at the baryon number, -1, +1, 0, right? So afterwards you have a baryon number of 0. And so the charge and the baryon number is 0. Annihilation is pure energy after that point. Now, the strange quark is a little bit different because the strange quark interacts with all 4 fundamental forces: gravitation, electromagnetism, weak, and strong. And so, if you look at the comment down here, all quarks have the strangest number of 0. The strange quark has the strangest number of -1. It's the only one like that. Okay, now the other category, if you look on your equation sheet, is this is on the right-hand side. They unpack leptons, and you guys know one of the leptons at least. There are 6 types. We have the electron, which we're very familiar with, the charge of -1. And then we have an electron neutrino, and so you've actually seen that as well. We just didn't put the little e there. The muon, and so it's kind of nice, the Greek letter mu. So it's the muon and the tau, and they are corresponding neutrinos, the muon neutrino and the tau neutrino. Now, the muon is actually heavier than the electron. The tau is heavier than the muon. So if you work your way from left to right, you're working, it's heavier. So the tau is heavier than the muon. Muon's heavier than the electron, and they're all a charge of -1. Now, it turns out that the neutrinos have a very, very, very small amount of mass. And it's been proved that they have a small amount of mass, but a crazy small amount of mass. And they're very hard to detect. We have billions of them going through us right now because in the sun, in the reactions of the sun, they shoot out and they're passing right through us without being detected because there's no charge, so the electromagnetic force is not interacting, right? And they have a very, very small amount of mass. They just pass straight through. So all leptons interact with the weak nuclear force, and that's important as well. And so, out of all 6 leptons, the top row is the only one that interacts with electromagnetic force because they're the only ones that have charge. Now, all the leptons, just like the quarks, have their antiparticles. So you have an anti-electron, which is a positron, positively charged electron. You have the anti-muon, the anti-tau, as well as the anti-neutrinos, which we've seen before too, right? The anti-neutrinos of each of these. Now, all leptons have a lepton number of 1. Anti-leptons have a lepton number of -1. And we know that all the lepton number must be conserved, just like the baryon number. So let's say we had an electron and an anti-electron or positron, same thing there. what would happen, right? So if you think about it in terms of charge, the electron's -1, the anti-electron would be +1. So we bring those together and we get 0 charge, right? With the lepton, we add up the lepton numbers and we get 0. So again, we get annihilation, right? The electron and the anti-electron annihilate, and we're left with energy again. Now, what's interesting in this with the electromagnetic force, classically, what we've been talking about, is that the electric fields are pushing off each other. But actually, what's happening according to the standard model is that there's an actual exchange. So here's an electron, right? And this electron are both moving, and they interact with each other. They push off each other. This electron takes off this way, right? The other electron takes off this way. And what actually happens is there's an exchange of a photon. So this electron shoots a photon off like this. It hits this electron in conservation of energy or conservation momentum. They both head off, right? It absorbs it. This electron, however, when it shoots this off, it shoots off in this direction, conservation of momentum. And so really, in the electromagnetic force, we're dealing with the exchange of a photon, which should, it's sounds kind of strange, right? So again, the top electron shoots off, or shoots out a photon, and then goes to the bottom right, and then the bottom photon absorbs the photon and goes downwards. Now, Richard Feynman helped, well, he did a lot of things, but one of the neat things that he was able to do was communicate these very, very difficult ideas into ways that normal people like us could understand, right? Just people that aren't experts in particle physics. Now, these diagrams, are a little bit well, they're very helpful. They can get quite complex, and so we're just going to look at the very basics of it to look at that. Now, for the diagrams that you're going to see here, the time is going from left to right, and so you'll see that here. Now, the diagrams that I'm about to show you, the next 5, show the same thing if we look at it from the right angle. So, in other words, here, let's say you have an electron, right, and it absorbs a photon. Well, if it does that, it's kind of like a collision. These two collide together, they move off together, right? And so you've got that. Now, this one should look kind of strange because a positron absorbs a photon, right? Well, that's, if time is going from left to right, right? So here's time is going from left to right. It looks like these positrons are going against time and absorbing, right? It looks like, this photon or electron's going here, it's absorbing this and then going this way, right? Well, it's not exactly that way. So we're not really moving back in time. That was one of the things as I was working back through this. I wanted to find a good explanation of what's actually happening and why the diagrams are the way they are. So I'll give you, well, you can go ahead and pause the clip and read through this and then put the underlying things in there. And I think that'll help you understand a little bit more about these diagrams. Okay, so in this case here, an electron emits a photon, right? So this electron is going up, and as it emits a photon, right, this one shoots down like this, conservation momentum. This one, right, a photon actually materializes, right? So you have energy materializing into matter. You have an electron coming out as well as a positron. Now, if you notice here, anytime you have an antimatter, an antiparticle, their arrow is going to be pointing against time. And like we saw in that last clip, it's not really going backwards in time. But for this to be represented correctly, it's got to be going backwards. And so likewise with this, if an electron and positron collide together, they annihilate each other and a photon's produced of energy. You've got that here, the electron and the positron collide. Now, what's interesting about this is in all of these pictures, notice what happened with the arrows. This arrow is continuing like this. This arrow continues like this. This arrow, both the arrows are continuing. This one, both arrows are continuing. This one, both arrows are continuing. And then you have the photon out there. This is actually the exact same picture. If you rotated all of these and looked at them, they're all the same picture. And so back to that quote that I just showed you, this is showing that, maybe it's just the same particle, but going backwards and forward in time. And so, yeah, hopefully that helps with the intuition there. So now what we're going to take a look at is this idea of annihilation. We've already looked at two examples, the antiproton and the proton colliding, and then energy being produced. Same with this electron and anti-electron here. So annihilation, occurs when, you have, the two annihilate and then you have something being produced. Now in this case, this is kind of interesting. You have an electron and a positron colliding together. That becomes a photon. And then that photon becomes a particle and an antiparticle after that are produced. So afterwards, you have a new particle and an antiparticle that are going out. And so that's an important idea where you can go back and forth from energy to mass, right? What we looked at in that earlier, earlier in nuclear, where mass and energy are interchangeable, right? So, yeah, so it's an important idea here. Now we know, and this I probably should have had earlier. What these pictures are called are interaction vertices. So interaction vertices are what these pictures are showing here. We looked earlier at electron scattering, where we had an electron push off the other one, and the medium, the exchange particle, was a photon, and that's what we call these, the exchange particles, where this electron exchanges, it sends the photon, and this one absorbs it and shoots off. Okay, so now we're ready to talk about the three exchange particles for the weak force. We kind of brushed over the weak force earlier on, but now we're going to unpack the weak force a little bit more. Unlike photons, these particles, the W and Z bosons, do actually have mass. And so if we take a look at the four fundamental forces, this is the bottom of your equation sheet. It's kind of nice. They unpack each of them for you. You have the weak nuclear, you have the gravitational, weak nuclear, electromagnetic. You also have the strong force. They also talk about the particles that are interacting. So that's really nice. With a weak force, there's a lot of different examples. We'll just look at a few here. Let's say you had a down quark that turned into an up quark, right? Let's say in a certain decay. The W boson can be responsible for making that happen. And so that's what that's showing here. The up quark becomes a down quark because of this W boson. This electron, right? This electron now becomes a neutrino, electron neutrino, and a W boson shoots off. And so, yeah, so you're kind of seeing the flow in time here. Now, this is the one that I wanted to focus some more attention on. If you remember in beta minus decay, right, we talked about how, you have a neutron, and in that nucleus you have too many neutrons, right? And so the neutron becomes a proton. And we did that nuclear act outside where I said, okay, here's the weak nuclear force, the whole nucleus shakes and, all of a sudden a proton is formed out of a neutron. Well, the weak nuclear force is responsible for that, right? But it's actually, it's the W boson that's making this happen. So if you notice here, the down quark becomes an up quark. And that W boson is enacting that. Therefore, afterwards, an electron is produced as well as a anti-neutrino, electron neutrino. Even though the arrow is pointing, and we'll always have the arrow pointing to the left if it's an antiparticle, right? So it's pointing to the left, right? The electron's pointing to the right. It's shot off. And that should make sense, right? Because if you're starting with the neutral charge, then you end up with +1 here. You're going to have -1 to counteract, so you still have 0 charge afterwards, right? But now we're looking at how that boson is actually enacting that. We could have done this for beta positron decay as well, whatever example. So this is a little bit more involved example, but you could hopefully, see this, over time. This is changing this into this. This is changing this into this. This is, well, actually, these are staying the same. The down quark staying the same, the up quark staying the same. It's just the down quark here is changing into an up quark. So the strong force now, if we look at the final column here, has to do with the quarks being held together in the nucleus. And this is a really important idea, right? The quarks being held together. And it's actually the particles mediating this are gluons. These gluons are enacting this. So, we have the quarks, and these gluons are the exchange particles making this actually happen. And so, instead of a photon, right, between two electrons, the gluon itself is actually holding those quarks together. Now, something that we're not going to get into that goes a little bit further is the colors. The colors of these quarks and their exchange with the gluon inside is another critical part, if we were going a little bit deeper with that. Hopefully now you've got a good picture of each of the four fundamental forces and what's going on. Now, we do want to talk about the gravitational force. Turns out the exchange particle for gravitational force is a hypothetical particle called the graviton. And if it exists, it's expected to be massless and have a spin. Now, it's interesting because, with the gravitational force, if you look at the force of gravitation, right, we have, force is equal to gm1m2 over r squared, right? So you have forces between masses. Now, in terms of the whole standard model, this is still, how does the gravitational force fit in with the standard model? It's still tough. So they're still working through this. Now, the other force that we want to definitely talk about is the electromagnetic force. The exchange particle is a photon. You have the gamma ray, symbol here representing for a photon, and that's the exchange particle with the electromagnetic force. Okay, now with confinement, quarks only exist within hadrons. You can't have an isolated quark. I can't just hold an up quark in my hand or something like that, right? There's many things wrong with that, but you can't just isolate a quark on its own. Now, what's interesting about the, like a meson, for instance, if you had a quark in an anti-quark, right, and you're trying to separate them, they are not going to want to separate. And it actually turns out the further you try to separate those, the more energy that it's trying to hold to keep them together. It would take an infinite amount of energy to actually separate them. And so you can't separate them. You have to have those individual quarks. Now, the standard model of, is including all the things we've been talking about: quarks, leptons, the exchange particles. This is defining the standard model, and we have really good experimental evidence for this. Now, the missing link all this time was the Higgs particle, and what the problem was with the weak force. And so what happens with the weak force mathematically, it showed that that there is the photons, the W and Z particles of the weak force do not have mass. However, the W and Z bosons here, right here, okay, actually have a lot of mass. They have a lot of mass, and so that's a problem. And so they made the theory that there must be this Higgs field, and that this Higgs boson, this Higgs particle, must be here. And so they thought that really that Higgs particle is responsible for, through its interactions, that because of the Higgs particle and the Higgs field, we do have the W and Z bosons that operate, like the way that the standard model looks at. And so there's a really helpful analogy that looks at this. And it turns out in 2012, they did find it, and they measured it. They were actually able to get it at the Large Hadron Collider. It was predicted within the standard model a long time ago, but they finally were able to discover it. Now, this analogy hopefully will be helpful for you as you try to picture this. Let's say you're pulling a ball through the air, right, with a force. We know F equals ma, right? But we know that air is a fluid and it makes it slow down, so it can't be quite as fast as it normally would be. So that counteracting force makes the acceleration smaller than we expected, and that's kind of like if we had a ball that had more mass, but we didn't have air resistance. It would have more inertia, right? And so, it's showing that, you know, that ball, as it goes through the air, right, would have some of that air resistance, but it's just like if we had no air resistance with a little bit more mass. That's roughly how the Higgs works. And what I'm going to do is in the links here, I'm going to give you this video that you definitely need to watch, and then I'm gonna do the other one, hopefully with the standard model that I'm going to include in there as well, that give you a pictorial picture of what's going on with this, and that'll be good.